Okay, this is a review of atomic structure and periodicity. There's a lot on this slide, but I just wanted to remind you of the inverse relationship between wavelength and frequency, and that all forms of electromagnetic radiation, so everything mentioned over here on this side, do travel at the same speed, and we call that c, the speed of light. These two formulas, the speed of light, and then we see the energy of one photon of light, are on the formula sheet. So I just put a little excerpt of that. It's literally the first thing you see when you look at the formula sheet. So notice we have Planck's constant, which is h. So again, just plug that in. Speed of light is given, and then there's Avogadro's number. So Avogadro's number, sometimes people are looking for it on the reverse of the formula sheet where we see molarity and other things related to stoichiometry, but it's actually here with atomic structure. I did want to show you this problem. Typically, you might be asked, what wavelength of light would it take to rupture, a certain bond or break a bond, same thing. I came up with this question. The bond, we know oxygen gas has a double bond. Its bond energy is 490 kilojoules per mole. And the question is, what is the minimum wavelength in nanometers of light that has enough energy to break this bond? If this was an AP question, it would probably be asked in more than one. Like, this is kind of one big problem, maybe in a couple problems. But I just wanted to work through this with you so you could see the steps you would need to really think about to convert this. So notice that bond energy is still an energy value, so delta is an enthalpy value, 498 kilojoules per mole. If we go back to the previous slide, notice this energy formula on the formula sheet, this is a mistake kids make, is only for one photon. So what we're talking about, a mole of bonds would need a mole of photons to break. So the first thing we're going to need to do is get this into a simpler form. So not a mole of bonds, we need one bond. So we need to change kilojoules per mole to joules per photon. Then we can use this energy formula. Once we have the energy formula, again, I'm going to go back. Once we can use this energy formula, if we have the energy of one photon, or the energy of one bond that would correspond with the energy of one photon, then we can find frequency. If we know frequency, then we can substitute that in and find wavelength. And after we know wavelength, we can get it to the right unit of nanometers. So that's where this is going. It's a very kind of long process. Notice here we convert kilojoules a mole to joules per photon, so that's where we need Avogadro's number, and then the relationship between kilojoules and joules. So notice this number is a very small energy value, and that is for one photon or one bond. Number two, after we have the energy of one bond or one photon, we can change that or convert that to frequency. So notice I've plugged in my answer from the previous problem to energy. There's Planck's constant from the formula sheet, and I'm dividing energy by Planck's constant to get frequency, and the units are 1 per second, or hertz is what we call that for frequency, inverse time. All right, now number three, we've got to take that frequency information and change it to wavelength, because we're asked about the wavelength of light. So there's the speed of light plugged in. We've got our wavelength symbol, and then our frequency. So again, now I'm dividing again. Speed of light divided by frequency gives me wavelength, and I see this answer. There are 1 billion nanometers in a meter, so I know that that's going to end up as 240 decimal point, 3 significant figures, nanometers. The quantum model of the atom really is trying to explain where electrons are most likely located, and they can only be in certain locations around the nucleus. And I've seen this compared to like books on a shelf. The books can only go on the shelf, they can't go between the shelves. So think of this as electrons can only go in certain energy levels, they can't be in between the energy levels. So we call energy levels numbers. We number from the nucleus out. So you see the 1s orbital is closest to the nucleus, then the second energy level, and as you go out it gets a little bit more complicated. Now we have s and p orbitals to get to the third energy level. We have s, p, and d, and then they start kind of overlapping a little bit. The 4s orbital is a little bit less energy than 3d, and then, it goes on from there. You do need to be able to write an electron configuration or use an electron configuration to identify an atom or an ion. So here's just a general guideline. The whole number in front tells us the energy level where the electron's located. The letter tells us the type of orbital or the subshell where the electron's located, and the superscript tells us how many electrons are in that specific position. Remember, s orbitals can only hold 2 electrons. P orbitals, since there are 3 orientations, can hold up to 6. D have 5 orientations that can hold up to 10. F probably won't see, but 7 orientations that can hold up to 14. So here's examples of ways to represent where electrons are located. The most common would be our electron configurations, where we do the 1s2, 2s2, and again, you might have learned this using the periodic table. It's pretty easy that way, where the energy levels correspond to the periods and the letters correspond to the different areas on the periodic table. Orbital notation, or an orbital diagram, is we're actually drawing an arrow to represent every electron. So it's very similar to electron configuration, except that you draw a box or a line, and instead of writing a 2 here, we're actually drawing the 2 electrons in that position. Same thing, so you can see that the 2s2 corresponds with 2 arrows, and then when we get to, then again, these aren't the same configurations, but when we get to this, notice it's 2p4, 4 total electrons, but there are 3 orbitals at that 2p level. Notice the way this is filled, this is based on Hund's rule. Each electron will receive each orbital will receive 1 electron, and then we would go back and pair them up. And that's why there's only 1 pair instead of 2 pairs. It's like I use the analogy of dealing cards. And the noble gas notation, not super important, but basically you would take the noble gas that the previous energy level ended with. So if you looked on your periodic table to krypton, and then the next row on the periodic table after that, or the next energy level of electron, starts at the 5th period or 5th energy level, and you could count over into the 4th element of the P block, and you would see the identity of that element. Here's a couple of practice problems, because you probably would be asked for an ion. So notice negative ions gain that many electrons, positive ions have lost. So if you did oxide and then zinc and zinc 2+, notice oxide would be expected. It had, if it was an atom configuration, it would be 1s2, 2s2, 2p4. It's gained those 2 extra electrons to fill that 2p orbital, so now it's 2p6 for oxide. Zinc is a transition metal, and again, I wanted to point this out. This has been on the AP exam before, not necessarily that ion, but other transition metals. If transition metals form ions, their first 2 electrons that are lost are from the outermost s orbital, not what's expected. We might expect they would lose d electrons first, but notice it's the 4s electrons that are missing. Those are the electrons that are actually take the less energy to be lost. Those are considered its valence. So if it's losing 2 electrons, it'll lose the outermost s electrons first. If it was an ion, maybe like Fe3+, that could lose an additional electron, it would lose it from the d. The atomic radius trend, again, it's nice to see the picture to kind of see the trend. No one's going to ask you necessarily what the trend is, and the trend is not an explanation. We'll go over that. Notice as we go across a period, the trend is that the size of atoms gets smaller, and as we go down a group, the size of atoms gets larger. We have to explain why is that the trend. Okay, so right here, if asked to explain why a calcium atom is larger than a magnesium atom, again, look at your periodic table, see where they are in relationship to each other. Don't say as you go down a group the atom size gets bigger. That's not going to give you any credit if this is a free response question. The reason is, if we're doing a group trend, we need to mention energy levels of electrons. That's going to be our explanation. So calcium has valence electrons. Don't say calcium is in the 4th energy level. Calcium has its valence electrons in the 4th energy level. Magnesium has valence electrons in the third energy level. Since the valence electrons of calcium are a greater distance from the nucleus, that means they're less attracted, and that expands the cloud. That makes the cloud larger. And again, if we're comparing sodium and magnesium, again, see where they are in relationship to each other. They're right next door to each other. Magnesium's to the right of sodium in its period. Again, a period trend, we're going to need to mention effective nuclear charge. An effective nuclear charge refers to the positive force that's attracting electrons that's coming out of the nucleus. So we would say magnesium has one more proton than sodium, and you could say it has 12 protons versus 11. That's saying the same thing in two different ways. So what does that mean? Well, it means that magnesium has a stronger effective nuclear charge, which causes a greater attraction for its electrons in that same energy level, which pulls in the size or makes the size a little bit smaller. The term isoelectronic, iso means the same. These could be an atom or a series of ions that all have the same number of electrons. You can see that in the picture, like oxide, fluoride, neon, sodium ion, and magnesium ion. You might be asked, which of these is the smallest size? You can look at the proton to electron ratio that's mentioned, but it really boils down to which one has the higher effective nuclear charge, and it would be magnesium. Magnesium ion has the most protons. You would want to say specifically the value, and then you could compare it to one of the other ones. Ionic radius. Notice the pictures kind of give you a good depiction of this. When a neutral atom loses an electron, its size decreases, and when a neutral nonmetal atom gains an electron, its size increases. And again, you might have to explain why. So for lithium and lithium ion, we would want to talk about where the electron is located that is lost, because when lithium loses a valence electron, now it has one less energy level of electrons. So you'd want to mention it loses its 2s electron. Now, as a lithium ion, it only has the electrons in a 1s orbital, or the first energy level. So that difference in energy levels is what's causing this huge size. Now, when you get to the chlorine and the chloride's just gaining an electron. There's no difference in energy levels. It's a difference in, you have, again, they both have the same number of protons. When there are more electrons, there are more electron-electron repulsions. In other words, those same protons can attract one more electron with as great an attractive force as the atom can. So there's some repulsions happening that are making the size expand. And again, that's also mentioned here. This question was actually on the AP exam last year with the iron comparison. Why is Fe2 plus a larger ion than Fe3 plus? And the credit was given only for saying Fe2 plus has one more electron than Fe3 plus, which causes greater electron-electron repulsions, which expands the size. The ionization energy trend is the opposite of the size trend or atomic radius trend. So as the size gets smaller, it's going to take more energy to remove an electron, and so that would be across and down the group. So here's the definition of ionization energy. It's the energy required to remove an electron from an electron, and we do talk about numbers here, like the first ionization energy, the second, and again, whatever numbers referred to, it's that number of electrons. So if it's the first ionization energy, it's the energy to remove the first electron. Second ionization energy, the energy to remove the second. If you look at the table, it's gone all the way up to the fifth. What you're looking for in a table like this is a huge jump. We expect ionization energies to go up because every time an electron is lost, what's remaining is a positive ion. So that's going to have a greater attraction for the remaining electrons. However, when you see a huge jump, and so we look at these, we've got 560, 1815, 2,740. I mean, those seem like significant jumps, but then all of a sudden it goes from 2,740 to 11,000. So this is really a dividing line, and the dividing line here is between valence electrons and then these would be core. Okay, so the valence electrons are in an energy level higher. They do take, in this case, increasing amounts of energy to remove. Once you get to all the valence electrons being removed, the jump is significant. So that you should draw a line where you see that huge jump. And when it asks you the question, what element is X from the third period, you go to the third period, count over, figure out which element in the third period has 3 valence electrons, and then you have your answer. And in this case, it is aluminum. Ionization energy trend, again, don't state the trend as we talked about earlier with atomic radius. Explain why. So if we're talking about magnesium and calcium, again, this is a group trend. So just as before, we need to talk about energy levels, where these electrons are located. If magnesium's ionization energy is higher than calcium, that means it's smaller. But we gotta talk about how that's happening. And then for the second question, magnesium and sodium, magnesium's is higher. That means its electrons are more attracted. Why? So that's a group trend. We're going to talk about energy levels and where they're located. A period trend with this second one, we're going to talk about effective nuclear charge and how that relates to this. So, calcium has valence electrons in the 4th energy level, magnesium in the 3rd. Again, this sounds very similar to what I said before, but we just have to relate it to ionization energy. So, since the valence electrons of magnesium are a smaller distance from the nucleus, that means they're more attracted and would require more energy to remove. So again, it's more attracted, requires more energy. With magnesium versus sodium, again, this is our effective nuclear charge. We said magnesium has 1 more proton than sodium, so magnesium has the greater attraction for those electrons in the same energy level, and it's going to take more energy to remove an electron from magnesium. There are types of spectroscopy. You can kind of read over these. Mass spec, we talked about isotopes in the stoichiometry review. PES really is evidence of these electron configurations and explains why ionization energies are different values. And then some of these other ones are not quite as, and we do use, my class uses a colorimeter, maybe use a spectrophotometer, but that's where we use Beer's law and use colored solutions. But these last two, we don't have any really experience with these. IR, think of infrared, so think of heat as vibrating bonds. I'm just trying to give you something to associate this with. And then microwaves, more energetic. It can actually rotate the molecules. Here's an example of a PES thing. You might actually see the data for this. And so, again, the higher the energy numbers indicate electrons that are more attracted, closest to the nucleus, take more energy to remove. And then the height of the peak indicates how many electrons are in that position. So we could actually go through and start writing electron configuration. So find the highest number. That's 1s2. The next highest number should be 2s2. And then notice this is taller. That's 2p6. And then this must be 3s2. So that tells us that this must be, and that's the first question, magnesium. And which peak represents the valence electrons? It's going to be the lowest energy number. Just be careful if it's like a p block element that you realize there would be more than one peak of valence electrons. So there'd be s and p valence electrons. Here's an example of kind of a different version of a multiple choice question that's been on an AP exam. So this is saying we have 2 isoelectronic species, calcium 2+ and argon. Okay, so they have the same number of electrons. Obviously they're very different. Which of the following correctly identifies the species associated with peak X? So notice peak X has a higher, they're both the same height. That's not what it's referring to. Peak X is a higher binding energy value. So that means the electrons for X are more attracted to the nucleus. So what causes electrons to be more attracted to the nucleus? And really, what's the difference between calcium and argon? it's protons. So which one of these answers refers to effective nuclear charge or protons? That's what we're looking for. And you see that it is D. More tightly held electrons have a greater attraction to the nucleus and take more energy to remove. So it is calcium. A lot of times people want to just pick argon because it's a noble gas, and we always think of those as special. But again, in this case, calcium has 2 more protons. It does have the higher attraction. The reactivity trend, notice metals get more reactive down the group. Nonmetals are opposite, because think of fluorine at the top of the halogens is the most reactive nonmetal. And then here just some general properties of metals and nonmetals that you probably know, just as a good short review.